We have here a map of the states of the bottle engine. We start at a volume V0 and P0. This is state 1. Okay, volume V0, pressure P0. These are written rather badly. They're a little hard to read. But that stands for V0, P0 is the state of the system. And V0 we're taking to be 1,000 milliliters this time. P0, atmospheric pressure, rounding off to 100 kilopascals. So let's kind of zoom in on that part of the diagram. You see what I mean about the V being written fairly poorly. Now, what happens when we start adding thermal energy? Well, what happens is, as we've seen, the pressure increases and the volume doesn't. So that we have this vertical line here on the pressure volume graph. Pressure increasing at constant volume. The pressure increases to 100 kilopascals plus rho GH. Okay? And we've seen that the rho GH comes from the fact that we have to have enough pressure to hold the water up the tube. Okay? P0 plus rho GH, and that's going to be our state here. So that this distance here is going to be rho GH. The change in pressure is going to be rho GH. And I'll note, incidentally, that this is not drawn very well to scale. Matter of fact, I probably ought to put a little break in the axis here and a little break in this axis here, because the pressure increase here looks like it's greater than the original pressure. Looks like we started out at atmospheric pressure and ended up at over twice atmospheric pressure. And we certainly didn't do that with the system that we observed. We didn't have enough thermal energy. Well, we had plenty of thermal energy, but we didn't have hot water. We weren't able to use, with the plastic bottle, we weren't able to use hot water or any source of thermal energy that would be capable of raising water to this height, which would have been well over 10 meters. We could raise water about 1.5 meters, and that was about it. So we'll put these little breaks in here so as not to be misleading. If we drew the diagram completely to scale, we wouldn't have room to label it, because this height would be very tiny and this width would be very tiny. Okay, anyhow, we have a state 2 here, which is still at the original volume V0, but at pressure P1, which is an increase of rho GH over the original pressure. Then what happens? Well, let's stop a minute. We got T equals question mark here. We can easily find temperature T. It's just going to be in the same proportion to the original temperature. Okay, the original 297 Kelvin, or T0 if we wish, as pressure P1 is to P0. So we're just going to use the pressure ratio to find the temperature here, as we've seen. Then we allow the water to overflow, which increases the volume of the system, moving the graph in this direction without any increase or decrease in the pressure, which would be up or down on a pressure versus volume graph. And we end up at volume V3 and pressure P3. P3 is actually the same as P1, and really what I call P1 I should have called P2, the pressure at state 2. That's a little misleading, and let me change that here. And let me go back. And make the same change here. And here. You might want to make that change in your notes. Okay, I think we want to say that we got original pressure and volume, but that's really V1 and P1 is really the same as V0 and P0. At state 2, we're going to call it pressure 2, volume 2. We'd call our temperature T2. Okay, anyhow, in the final state, we're at a volume V3 that we can get by simply looking at the ratio of temperatures between state 2 and state 3. We know the temperature is state 3. State 2, as we've seen, is a state in which we can easily find the temperature. In a minute, we're going to look at the energy changes that go on in this part of the process.